Okay, so the main result of our discussion is basically this one. So eventually we would like to calculate the matrix elements of products of fields in the vacuum, the time-ordered products of the fields in the vacuum. These are the fields of the full theory, the interacting theory, and the vacuum is the vacuum of the full interacting theory. And this we can write as the time-ordered product of the same fields. Let me write phi 0. Here on the left-hand side, omega is the ground state of full theory. Zero, this is the empty state, or ground state of non-interacting theory. And phi zeros, they are the interaction picture operators. They evolve under the non-interacting theory. So they are essential solutions of the non-interacting theory. All the interactions, all the effects of the interactions are in these exponents. Now, of course, the problem is how do we calculate these things? Well, I will drop the zeros, I will drop the interaction picture I, so from now on, whatever we do will be in the interaction picture. So let's start with the Feynman propagator. We had already calculated it. This is 0 using one method. Remember our derivation, we had this time-ordered product of phi of x1, phi of x2. We wrote this time-ordered product explicitly in terms of the unit steps, step functions, and we wrote our fields phi x1 and phi x2. We wrote their explicit expressions, and then we just use this counter integral trick to write the step function as an integral over some complex, some closed counter in the complex plane. But let's look at the same problem from a slightly different perspective. So this will be equal to, but before continuing, let me just write phi of x in two parts, phi plus phi minus, where phi plus is d cubed k divided by 2 pi cubed, 1 over square root of 2 omega k, a k dagger, e to power minus I kx, and phi minus x is d cubed k divided by 2 pi cubed, 1 over square root of 2 omega k, a k e to power I kx. Plus contains all the creation operators, minus contains all the annihilation operators. Now, why did I want to do that? Well, let me just write the time-ordered product in terms of these plus and minuses. Theta x1 0 minus x2 0. If the time of x1 is later, then it will be phi plus x1 plus phi minus x1 times phi plus x2 plus phi minus x2. If the ordering of the time is the other way around, I just change the order of the operators. Acting on the empty state. This is the definition of the time ordering. Now, 0 phi plus x is 0 because they contain the creation operators. So if they act on the empty state from the right, it will annihilate the bra, so this will be 0. Similarly, phi minus acting on 0 will be 0. What that tells me is this term doesn't contribute. That is a phi plus acting on the bra, the empty bra. This term doesn't contribute. It will be the annihilation operator acting on the vacuum. This will not contribute. Again, annihilation operator acting on the empty state. And this will not contribute. Again, the creation operator acting on the bra from the right. So I will not have many terms in my expansion. I will just have a few.
Hocam, 1/2 term, wouldn't it be because we, just calculated the, x1 0 before x2 0 and the reverse of that 1/2 term just,
What is 1/2? Where?
Arises, because of the correlation function.
No, this is the definition of the time ordering. There is no 1/2 in the definition. It's just either one ordering or the other one. Now let me write phi minus x2 phi plus x1. Now the reason why I put that empty space is let me just subtract those terms multiplied in the reverse order. Basically, I'm replacing those products by commutators. Just in a moment. Those terms are 0. They're just annihilation operators acting on the vacuum. But then I have this one. The commutator of two fields. They're equal. Well, the commutator is a C number. It's not an operator. I can just take it out. So this matrix element is equal to theta and this is what I had already calculated. I know the form. Well, that time-ordered product will just give me some commutators. Yeah, I didn't really achieve much. I still need to calculate those commutators, etc. But now let's look at the higher-order term. You see, these terms, now look at this matrix element over here. To calculate it, I need to expand that exponent, and I will get many terms. I need to calculate them all one by one. So, for example, if I want to calculate let's say if I want to calculate this thing only, I should expand this exponent, multiply by two fields. I will have many terms there. the first term will have just the time-ordered product of two fields. The next term will have, I don't know, depending on what kind of interactions I will have the product of 4 fields, 6 fields, etc. Eventually, I will have the products of many fields. So this is just the time-ordered product of 2 of them between the matrix element in the empty state. Now let's look at what happens if I have 4 of them. I'm not looking at that one, but let me look at this one. Well, what I need to do, I first have to write each one as phi plus phi minus. Write out the time-ordered product, and then move all phi pluses to the left, all phi minuses to the right. Let me, just as an example, x10 is larger than, let's say, x20. Or even, let's say, x30. Then I will have some terms. I don't know what they are. I mean, if x20 is even larger, it will be those terms will be even towards the left. But I will have phi plus x1 plus phi minus x1, some other terms, and then I will have phi plus x3 phi minus x3. Now what I need to, of course, this is the vacuum matrix element. What I will need to do is, well, phi plus will remain there. I will move phi plus towards left, towards the vacuum on the left. But phi minus, I have to move it towards the right. So I will commute with whatever appears in between. Eventually, I will get a contribution from again phi minus x3. I will move it towards all the way to the right, so that phi x1, phi plus x1 doesn't have to commute with any phi plus or phi minus x3. Neither phi minus x3 needs to commute with any of the phi plus x1 or phi minus x1, but I have to have phi minus x1 commuting with phi plus x3. That will be a term like that. Among many terms that I will receive, I will get a term in which these two should commute. I should consider their commutator. So this will be equal to whatever appears before times commutator of phi minus x1 and phi plus x3. Remember, this is just a C number, so I can just take it out. This is the only commutator term I will get between phi minus x1 and phi plus x3. Remember, I'm moving all the phi minus to the left, all the phi plus to the right. So I will get all these commutator terms. And when I move phi minus all the way to the right, I get 0. Or phi plus to the left, I get 0. Those will give me 0. Only if there are such commutators, I will get non-zero contributions. So what does this tell me? Basically, if x10 is larger than x30 in this time-ordered product, I will get a term phi minus x1, phi plus x3, this commutator, which is a C number. Inside, I will have phi of x2, phi of x4, and then I will have other terms which do not involve the commutator of phi x1 and phi x3. Remember, this is if x1 is larger than x3. Well, if x30 is larger than x10, if this is the case, well, basically, the only thing I need to change is within this time ordering, I can put x3 to as the first, phi x1 as the third term in that product within the time ordered product, because I mean the ordering doesn't matter as long as I'm inside the time ordered product. It just will tell me just change labels 1 and 3. So what did I obtain? This time-ordered product is actually theta x10 minus x30, phi minus x1, phi plus x3, plus theta x30 minus x10, phi minus x3, phi plus x1 multiplied by this, the other fields, time-ordered product, matrix element, plus other terms. But I know what that expression is. This whole thing is nothing but my Feynman propagator. And also, by the way, this is also my Feynman propagator. What remains turns out to be my Feynman propagator, let's say. Well, what happens if I have more than 4 fields, 6 fields, 7 fields? Well, basically the same thing. Here I just took 2 of them. I said that, okay, somewhere they have to commute, either phi minus x1 and phi plus x3, or phi plus x1 and phi minus x3. They have to commute somewhere, and I have to sum all their contributions. The same is true for the other fields also. Now, usually we have a shorthand notation for that. This term, what we had shown here, is actually equal to I'm just looking at x1 and x3. This turned out to be, this is the symbol we use. So this basically, that symbol basically tells me to write down the contributions only from the commutators of phi x1 and phi x3 without touching the other fields. And this contraction turned out to be the Feynman propagator times whatever remains. Now, what is the general term? This is equal to sum over all possible contractions. Well, what does that mean? I have, let me just write it once more. This is one possible contraction. Yes, always keep in mind that when I'm calculating this matrix elements, I will just commute all the annihilation operators to, coming from all of those operators to the right, all the annihilation all the creation operators to the left. So they will be commuting among themselves. There will be all possible commutations between these fields. These are the terms that will come from the commutations of phi of x1 and phi of x3, and at the same time phi of x3 and phi of x4. But then I also have commutations between phi of x1 and phi of x3 and phi of x2 and phi of x4. And also commutations between phi of x1 and phi of x4 and phi of x2 and phi of x3. What do those commutations give me? Well, the Feynman propagator. So this is nothing but x1, x2, x3, x4. This is the first term. The second term is the Feynman propagator between x1 and x3 and x2 and x4. And the third term is the Feynman propagator from x1 and x4 and Feynman propagator between x2 and x3. This is the result of that matrix element. And we can also show that diagrammatically. You see, basically, here I have what's called a 4-point function. There are 4 different points. Let's say 3 and 4. This is the Wick's theorem. What Wick's theorem tells me is just consider all possible connections between these dots. So there's this connection plus this one. Yeah, let me ignore the errors for the time being. There is this one. And there's this diagram. Each one of these lines connecting any 2 dots is just a Feynman propagator.
They are Feynman diagrams.
These are called Feynman diagrams. You see, once you have this Wick theorem, well, I can basically calculate to any order without much effort. Now let's get our case. Remember, we had this V given by lambda d4 d cubed x phi 1 r phi 2 r phi 3 r, no, phi 1 r. Just 2 kinds of particles, type 1 and type 2. Each having their field phi 1 and phi 2. This is our interaction this is our potential, or the interaction Lagrangian density is minus lambda phi 1 of x, phi 2 of x, phi 1 of x squared, phi 2 of x. This is my interaction Lagrangian. Now let's calculate, to calculate the scattering, we need to calculate this matrix element. If we can calculate this one, then we know how to calculate the S matrix element using the LS reduction formula. Well, I know what this is. This is just vacuum matrix element of time ordered product of my fields e to the power I d4x, the interaction Lagrangian, divided by time ordered product of only the exponential. What do I have? Let me just look at the numerator first. Well, what is this? I have 0 time ordered product, phi 1 of x1, phi 1 of x2, phi 1 of x3, phi 1 of x4. I had already calculated this. Then I have plus I d4x lambda phi 1 of x1, phi 1 of x2, well, the same phi's. Then I have phi 1 squared of x, phi 2 of y. Then I have plus I lambda squared over 2 factorial. There's a minus here. Minus I lambda squared over. Minus is from because the interaction Lagrangian density has minus lambda. d4x, d4y. Let me be a bit lazy. Phi 1, no, sorry, this is also x. Phi 1 squared y, phi 2 of y. Well, we had already looked the first one. It just is these three diagrams. Now there's actually no scattering here. Then we have this term. Now let me just put the points. I have x1, x2, x3, x4. At each one of these x1, x2, x3, x4s, I have one phi 1 type particle. Let me just draw a partial line over there. Remember, phi 1 kind of particles, I'm using them using lines. Phi 2 kind of particles, I'm showing them as wavy lines. Now there's the point x. This is my point x. But at the point x, I have two phi 1 kind of particles, one phi 2 kind of particles. So at the point x, I have these lines. What I'm actually doing is I have my mathematical equation. I'm just drawing it as a picture. This part over here basically tells me that I have phi 1 of x squared, phi 2 of x. They are at the point x. This point over here tells me that I have phi 1 of x1. Now I have to consider all possible contractions without leaving any open ends. Well, let's see, the easiest one possibility is this one. Now this is one option. But now there is one open end, one field that is not contracted with anything. That cannot happen. That is 0. Now, if you actually calculate this, this will be proportional to this matrix element. Which is 0. Just a single phi field. I mean, since we are looking at empty state matrix elements between empty states, there shouldn't be any fields left. So this will be 0. There is no contribution. This term, the second term, is exactly equal to 0. Now let me try to draw the last line, this one. Well, again, I will have 1, 2. These are my first kind of particles. And I have, let's say, 3 and 4. These are my, again, first kind of particles. I have a point X where I have 2 straight lines, 1 wavy line. I have a point Y where, again, I have 2 straight lines, 1 wavy line. Contractions basically tell me that I should connect these lines somehow. Every line should be connected to one other line of the same kind. I cannot connect wavy lines to straight lines. And there shouldn't be any open ends, because if there are open ends, we are back to this case. The only contributions I will have will be those without any open ends. Now, what are the options? Well, there is this case. All the phi 1 fields at the point X is connected to the 1 and 2. All the phi 1 fields at the point Y are connected to 3 and 4. And these phi 2 fields at X and Y, they are connected to each other. This is one possible diagram. I have another possible diagram. You see, phi 2 fields at the point X and Y, they have to be connected to each other. There are no other options. So this is definitely that. There is definitely that connection. Well, I can have the field at the point 1 connected to the point X. The field at the point 2 is connected to one of the fields at the point Y. And then the other field, the point 3 is connected to Y. Point 4 is connected to the line at the first line. Let me just draw it slightly better. I have 1, 4, 2, and 3. This is the line I have. And practically that's it, almost. Well, you see, for example, if we look at this diagram, I said that, okay, I can connect 1 and 2, both of those particles, to the fields at the point X. But I can connect 1 and 2 to the fields at point Y. And 3 and 4 to the fields at the point X. But it's basically the same diagram. Remember, I'm integrating over X and Y. X and Y are just dummy variables. I can change their name. If I change their names, I recovered exactly the same diagram as this one. So I have to multiply this diagram by 2. I don't need to calculate a second diagram. This computation and the other ones where X and Y vertices are exchanged, they will contribute the same thing. Well, the same thing also here. 1, instead of connecting to the point at X, it can connect to the point at Y. And 2 can connect to the other one. And 3 and 4, they will be the other way around. Again, a factor 2.
Why don't count, 1 interacting with first 3? What?
1 interacting with the What do you mean? 1 connecting directly to 3?
Yeah. Like, S, T, U, and the last channel.
So you are asking this one. Why don't we have, for example, no, not this one.
Yes.
So what kind of contraction is this? 1 is connected to phi field at the x. Okay, let me just count. Okay, so I can exchange x and y. That brings me a factor 2. Let me also remind you another contribution. If I look at the contraction of this phi 1, let me write one of these out explicitly, phi 1 of x, phi 1 of x. I can have phi 1 contracted with this phi 1 of x. I can have the same phi 1 contracted with this phi 1 of x. So even though 1 will be contracted with a field at the point x, there are 2 options there. Now let me look at this one. I said that 1 is contracted with x, with one of the fields at x. Well, I have 2 options. Even another 2. Why? Okay. 1 is connected to one of the phi 1 fields in x. 3 is connected to one of the phi 1 fields at the point y. There are 2 of them. Then 2 is connected with the field at the point y. There's 1 left, so there's no other factor 2. And 4 is connected to the remaining phi field at the point x. Again, there are no options, there's just 1 uncontracted field left. So let me look at this one. Oh, okay, yeah. One, two, three, 4. X and Y. The phi 2 fields have to be connected. There are no options over there. Now, 1 can be contracted with one of the fields at the point X. That's a factor 2. Now, 3, in this diagram, 3 is contracted with the field at the Y. But 4 can be contracted at that with the field at that point. Two fields left, so that's another 2 diagram. Now 3 can be contracted with the field at the point Y. 1 option left, so no factors. 2 can be contracted with the remaining field at the point Y. And of course, x and y, you can also change them. That brings down another factor 2. So if you look at this diagram, 1 connects to an interaction vertex and then is connected to 3. It is this one. And these are not all. We still have other diagrams. Let's say, for example, I can have, okay, phi 2 fields are contracted. This field is connected to this one, this field is connected to this one. And then you can have all the possible ways between 1, 2, 3, 4, or 1, 3, 2, 4, etc. So basically this will be, if you write the factors, you are just multiplying all those factors. What we obtain there is these diagrams. times 1, well, that was the original term we had, plus these ones. Well, that's not the only thing. I also have this one. Basically, 1, 2, and 3, 4. We can just imagine all possible ways of connecting them. That is this diagram. And basically, well, that's the computation. We have calculated, we know what to write. Each one of these lines is the Feynman propagator. Straight lines is the Feynman propagator for particle of type 1. Curly line is the Feynman propagator for the particle of type 2. Just multiply them, you get the corresponding contribution to your amplitude. Well, we still need to see what we will do with these. And we have keep in mind that we have this denominator over there. We also have to calculate that one and divide. That we will do on Wednesday. We'll just pick it up from here on Thursday. Okay. So any last questions before you go?
What do those loop diagrams correspond to physically?
What do you mean by physically? You see, you are not measuring any one of these. You are measuring the sum, the total of them.
This is a term in an infinite series. Right?
Yeah.
That's what it is. Yeah. And you're measuring a series.
So you see, this one is 1. This other term is the Feynman propagator of particle of type 1 between x and y squared. The Feynman propagator for particle of type 2, x minus y integrated over x and y. Plus, for this last term, I have integrated over x and y. Feynman propagator of the first kind of particle, x minus x. Feynman particle of the first kind of particle, y minus y. Feynman propagator for the second kind of particle, x minus y. Plus I have infinitely many terms. Now we will see what will happen to these again on Thursday. Well, those will basically turn out to be the denominator. So they are just cancelled. They don't contribute to anything. So see you in our next lecture.